Okay, good morning. Let us continue with tutorial number 10. This is a tutorial on combustion thermodynamics. The first problem, ethanol C2H5OH is burnt in a furnace with an equilibrium ratio of 1.1. If no hydrogen or oxygen is found in the exhaust, determine the product composition per kilomole of fuel. For the constant pressure process, determine the standard heat of combustion per kg of fuel. Okay, the standard heat of formation of ethanol is given as minus 235310 kilojoule per kilomole. So this is the, so let us try to write the equation first. C2H5OH plus 3 times O2 plus 3.76 N2. So this is stoichiometric reaction. Giving 3H2O plus 2CO2 plus 11.28 N2. Now actually we have equivalence ratio of 1.1 as given here. That means the equation is written as, so instead of 3 I would write 3 by 1.1. So we are supplying lesser air than the stoichiometric value. So now here it is given that the product composition has no hydrogen or oxygen. So that means hydrogen has fully converted into H2O. So I can write this. But CO2 is not fully converted. All the carbon is not fully converted to CO2. So I can say A times CO2 plus B times CO plus here I can write 10.2545 N2. So now I can find A and B values by, say for example, carbon balance gives in the left hand side 2 atoms. In the right hand side I can say A plus B. Similarly, I will take O balance. In the left hand side I have 1 O here. Okay, 1 plus here I can say 2 into 3 by 1.1. In the right hand side I have 3O here plus 2 times A plus B. So I have two equations and two unknowns, A and B. So solving I get A equal to 1.4546 and B equal to 0.5454. So now we can write the product stream. The product stream A and B can substitute and write it. So now I know the general equation, that is C2 actual reaction C2H5OH plus 3 by 1.1 O2 plus 3.76 times N2 giving 3 times H2O plus 1.4546 times CO2 plus 0.5454 times CO plus 10.2545 times nitrogen. So now standard heat of reaction, standard heat of reaction will be equal to HR minus HP. That is the enthalpy of reactant minus enthalpy of products, because the reaction takes place at constant pressure. So I can say delta H, the heat of reaction is HR minus HP. Okay, so actually this is HP minus HR, and this will be equal to minus of delta C, the heat of combustion, negative of heat of combustion. So now Standard means temperature of the reactants will be equal to 298 Kelvin. That will be also equal to the product temperature. So reactants are supplied at 298 Kelvin. After the reaction, products are formed and heat is transferred from the furnace to the surroundings so that the products are also cooled to 298 Kelvin. So under such condition, I get standard heat of reaction, which is the difference between HP, the enthalpy of the product mixture, minus the enthalpy of the reactor mixture. The enthalpy of individual species calculated at the reference temperature of 298 Kelvin. And the negative of that is called standard heat of combustion. So now I can write HR as HF of fuel, that is C2H5OH, plus I will say 0. Why? Because the standard heat of formation of O2 and N2, which are naturally occurring gases, will be equal to 0. Okay. Similarly, HP will be equal to 3 times HF of H2O plus 1.4546 times HF of CO2 plus 0.5454 into HF of CO, plus for nitrogen it is 0. Naturally occurring substance, so heat of enthalpy of formation is 0. So now for the enthalpy of formation of H2O, CO2, CO, etc., this is given in the problem. For the ethanol it is given. For the other species, we can use tables. We can also use some correlations if available. Basically, this is a typical table here. You can see that for CO, molecular weight is given, enthalpy of formation at reference temperature of 298 Kelvin is given as minus 110541. Okay. Similarly, if you want the enthalpy at different temperatures, that is also given. For example, the sensible heat, a sensible enthalpy minus the enthalpy of formation is also listed here. For 298, it is 0. Say for 1000 Kelvin, I can take the value. So this is the typical tabulation which we can get from several textbooks and reference materials. So this is for the CO. Similarly, if we go down, I can get for CO2, the enthalpy of formation is given as minus 393,546 kilojoule per kilomole. Similarly, I can do it for, so several species are listed, so I can take for water vapor and so on. So from the tables, I will retrieve the values of these and find the delta HR. So now delta HR will be equal to HP, which is nothing but 3 into minus 241,845 plus 1.4546 times minus 393,546 plus 0.5454 times minus 110541. This is the HP minus HR. HR is given as minus 235,310 and 1 kilomole is there. So I will say multiply by 1. So when you evaluate this, you get the value of HP minus HR as minus 1122966 kilojoule per kilomole of fuel. That means delta HC will be negative of this, 1122966 kilojoule per kilomole of fuel. So now we want delta HC per kilogram of fuel. That will be equal to 1122966 divided by molecular weight of ethanol. So that will be equal to 2441 kilojoules per kilogram of fuel. So you can see here, in the standard condition only the enthalpy of formation is used. To retrieve these values you can use some standard tables or NIST database. NIST database can be used. The second problem, in a constant pressure process, gaseous N-decane, especially given as gaseous because N-decane is in the liquid form basically. So we vaporize it and get the gaseous N-decane. Normal decay, that is C10H22, and the air at 298 Kelvin react to form dry products. The composition are given here. As I told in the tutorial 9, dry products means the water vapor which is formed is condensed and liquid water is removed. Find the heat of combustion if the product leave at 500 Kelvin. Okay, reactants come in at 298. So here the reactant temperature is reference temperature 298 Kelvin. Product temperature is 500 Kelvin, which is more than the 298 Kelvin reference temperature. Okay, now for this we have to first find the how much air is supplied, then we can find the values. Basically we don't even need to find the amount of air because temperature of the reactant is only 298. Anyway, for the air, oxygen and nitrogen will be elemental species, that is a basic natural element. So the enthalpy formation will be 0. So I can say delta HR will be equal to HP minus HR. Here I will say HR will be equal to, since the temperature of the reactor is 298, I will say this is HF of the N-decane, C10H22, that's it. Okay, because for the nitrogen and oxygen at reference temperature 298, enthalpy formation is 0. On the other hand, the enthalpy of products can be evaluated as, anyway we have to write the equation to understand how much CO2, H2O etc. is there, but here CO2 and CO can be found. So HP here will be equal to basically enthalpy of so number of moles of CO2 and HF of CO2 plus I will say delta H of CO2 at 500 Kelvin plus number of moles of CO into HF of CO plus delta H of CO at 500 Kelvin plus N of H2O into number of moles of H2O, HF of H2O plus delta H of H2O at 500 Kelvin. So please see that the overhead bar normally represents that it is per kilomole basis. Okay, plus N number of moles of N2 into here only delta H of N2 will come at 500 Kelvin plus N of O2 into delta H of O2 at 500 Kelvin. So here for the nitrogen and oxygen in the products, the enthalpy formation is 0, but sensible enthalpy which takes the temperature from 298 to 500 Kelvin will be included. So this is the thing. So now write the equation, chemical equation. So let us say let X moles of fuel is burnt for producing 100 kilomoles of, so for producing 100 moles of dry products. Why? Because if you add these percentages here, it will be 100. So I can say x times C10H22 plus, let us say, A times O2 plus 3.76 into N2 will give, I don't know the number of moles because it's dry product, so it's not known, but for others I can put the percentages of the given in the composition itself. So for example, for CO2 I will put 10.56 CO2 plus 0.92 CO plus 4.91 O2 plus 83.61 N2. That's it. So now I can find value of A and B by using atom balances, which we have demonstrated in the tutorial 9. Okay, so A and B values can be determined from this. So I will write the equation. Anyway, I will also divide by x. So x also can be determined. So x comma A comma B can be determined. So now once I do that, I will divide the equation by x and write the equation per kilomole of fuel. So there what I write is basically C10H22 plus 19.37 times O2 plus 3.76 times N2 giving 11 times H2O plus 9.1986 times CO2 plus 0.801 times CO plus 72.83 times N2. This is the equation. So now I know the number of moles of H2O, CO2, CO and N2. O2 also will be there obviously, plus 4.277 O2. So all this NCO2, NCO, N2, NH2O and NO2 are known now. From that I can calculate HP. As I told you, HR, it is only contributed by 1 kilomole of the fuel. So 1 into HF of C10H22. So the retrieving the values. So now please understand that I have to retrieve, apart from the standard enthalpy of formation, the sensible enthalpy also at 500 Kelvin. So now I will go to the tables again here. So for example, I will tell you take one case. So for example, CO, the enthalpy formation is 110,541 kilojoule per kilomole. At 500 degrees, the sensible enthalpy is 5943 kilojoule per kilomole. So I will say the standard enthalpy of CO will be equal to enthalpy of formation of CO plus delta H of CO at 500 Kelvin. So which is equal to minus 110541 plus 5943. That is the way I calculate. So that I get the value of the standard enthalpy and multiply this standard enthalpy, which is in kilojoule per kilomole, with the number of moles of CO. Okay, now the tables for several species is given. For example, here you can see this H and here OH and here H2O. So you can refer this table. Nitrogen. Nitrogen basically I don't want enthalpy formation to 0, but this value at 500 degrees, the delta H, that is the sensible enthalpy value, has to be taken. Similarly for oxygen. Okay, nitrogen molecule and nitrogen atom, then NO is given, then O2 is given here. Again I want this value for 500. Now, so if you see here, the fuel, the enthalpy of formation Gibbs free energy, etc. is given here. Here even the higher heating value, lower heating value, etc. are given here. We are now interested in getting the enthalpy formation of this. Okay, so the fuel is decane. So we can choose the decane and the enthalpy formation, that is this column here. For decane, this value minus 249659 has to be retrieved. So you can see that using these tables I can get the values. Now substituting the values, I will write the equation again. Specifically, H R equal to minus 249659 kilojoule per kilomole. That's all. This is only what? HF of C10 H22 at the standard condition and temperature of 298 Kelvin. That's it. Okay, enthalpy formation standard. Now what is HP? HP will be equal to 11 times minus 241845 plus 6947. This is standard enthalpy of water vapor. Okay, so this is HF of H2O and this will be delta T of, so delta H of H2O at 500 Kelvin. Similarly, I can write for CO2 9.1986 times minus 393,546 plus 8301 plus 0.801 into minus 110541 plus 5943, that is for CO, plus 72.83 nitrogen 0 plus 5920, because the enthalpy formation is 0 but sensible enthalpy is added, plus of oxygen 4.277 into 0 plus 6097. So, when I substitute this value, I can find delta HR equal to minus 5504486.2 kilojoule per kilomole of fuel, or delta HC will be equal to 5504486.2 kilojoule per kilomole of fuel. So when I divide by the molecular weight, I will get this as 38686.61 kilojoule per kilogram of fuel. So this is, here you can see that nitrogen and oxygen are present in the products, plus the temperature of the products are 500 degrees, not at 298. So the heat coming out is lesser. So this is about the problem where products are leaving at 500 Kelvin and the reactants are coming in at 298 Kelvin. So what I can draw here is, for example, this is enthalpy versus temperature. Normally you can say the enthalpy and temperature varies. This is for the reactants and this is for the products. Now, so let us say this is 298 Kelvin. Let us, this is in Kelvin and this is in kilojoule per kilojoule. Total enthalpy, so kilojoule. Now, this is the entry state. So I will say HR value, and this is 500 degrees or 500 Kelvin. Okay, now this will be the product. Okay, now this, so HP, this is HP. So now we are trying to find the difference between this and this heat. This is actually coming out of exothermic heat. So now please see that if the point comes down to 298, I will get more heat. That is called standard heat of reaction. And the products are leaving at any temperature. For example, here it is higher temperature. When the product leaves at higher and higher temperature, that heat coming out will be reduced. So this is what here illustrated in this. Now the third problem, a typical fuel gas mixture composition given. Again, we have seen this in the tutorial 9. 10% CO, 45% H2, 35% CH4, 4% C2H2, 2% of each O2, N2 and CO2. Evaluate the standard heat of combustion when the fuel mixture is burnt in stoichiometric air. Okay, so we have already seen that how to calculate the stoichiometric air. We have to write this in percentages and calculate by O balance, C balance, H balance, etc. the amount of air required. So, stoichiometric reaction is written as 0.1 CO plus 0.45 H2 plus 0.35 CH4 plus 0.04 C2H2 plus 0.02 times O2 plus N2 plus CO2 plus the oxidizer 1.075 O2 plus 3.76 N2. This is solved already, so I am just putting number, or we have to determine this value by using the atom balances. Giving the products also 1.19, the amount of, this is assuming that complete combustion takes place, so only CO2 and H2O are in the products, plus 0.55, sorry, this is H2O, 0.55 CO2 plus 4.062 times nitrogen. This is the equation. So now, how will you calculate the standard heat of reaction? Delta HR equal to HP minus HR. Now HR will be equal to enthalpy of formation of the fuel, but this is a mixture now, that's all, because for other oxygen and nitrogen in the air stream is 0. Even within the fuel there are some oxygen and nitrogen, so you can set hydrogen also is there. Okay, so note that enthalpy of formation of I equal to 0 when I equal to O2, N2, H2 and solid carbon, graphite. The enthalpy formation is set to 0. Naturally occurring elements, 3 are gases and this is carbon, graphite, solid. So, this is this. So, how will you evaluate this? This can be evaluated as a function of the mole fractions. Okay. So, the number of moles are given here. So, we can use the mole fraction and get the value of this. So, this will be equal to, or if we want to calculate in kilojoule per kilomole, just multiply the number of moles and this. For example, here I can say 0.1 times enthalpy of formation of CO plus 0.35 times enthalpy of formation of CH4, because this is 0, hydrogen is 0, plus 0.04 times enthalpy of formation of C2H2 plus 0.02 times enthalpy of formation of CO2. That is the enthalpy of reactant. So, again from the tables I can find the value of enthalpy formation of CO, CH4, C2H2 and CO2. HR is calculated like this. Then HP, okay, basically this into 1. So, this will be kilojoules only. This is 1 kilomole of fuel. So, here this is number of moles and this will be kilojoule per kilomole. So, this is a kilomole into, so again we get this, sorry, this is in kilojoules and this is in kilojoule per kilomole, sorry, this is in kilomole. So, multiply that, I get HR in kilojoules. Okay. So that is the thing. So now HP is what? HP is the products are only these three. So 1.19 times enthalpy of formation of H2O plus 0.55 times enthalpy of formation of CO2. That is for nitrogen it is 0. So now by substituting the values of enthalpy formation of the fuel species and the CO, CO2, H2 etc., I get delta HR equal to minus 468,200 kilojoule per kilomole fuel, or delta HC will be equal to 468,200 kilojoule per kilomole fuel. That is the answer. So we can see here that the mixture enthalpy is calculated, enthalpy formation is calculated by using the same mixing rule. The weighting is done by the number of moles of each species. Okay, now fourth problem, a liquid alkane, normal alkane, so CnHn 2n plus 2 is burned with dry air and the product composition in dry mole basis is given here. 9.6% CO2, 7.3% O2 and 83.1% N2. So here again H2O is not there because of the fact that the water vapor is condensed and removed as liquid water. What is the standard heat of reaction per kg of fuel and also per kg of oxygen, and also find the higher heating value. Okay, so we will do this solution. Let a kilomole of fuel burns to produce 100 kilomoles of dry products. So this means A times C n H 2n plus 2 plus B times O2 plus 3.76 N2 giving 9.6 times CO2 plus C times H2O, which I have determined, plus 7.3 times O2 plus 83.1 times N2. So now I can do the balances. So a N balance will give you 3.76 B equal to 83.1 implies B will be equal to 22.1. Similarly, O balance B is 22.1. So 22.1 into 2 equal to 9.6 into 2 plus C plus 7.3 into 2. So this will give C value as 10.4. 10.4. Then C balance N into A in the left hand side is equal to 9.6 plus 9.6, that's it. Okay, so now this is one equation which we have. Then for the H balance, 2n plus 2 times A will be equal to C into 2. So 2 times C, correct? So that is equal to what? 20.8. C is 10.4, so it's 20.8. So there are two equations here. I can substitute for Na equal to 9.6. So solving, I will get the values of N equal to 12, A equal to 0.8 kilomole. So that's what I will get. So now I can write the actual reaction is C12H24 plus 2, that is 26, okay, plus 27.625 times. Please understand that I have divided the equation by 0.8 so that A is kept as 1 now. So 27.625 times O2 plus 3.76 times N2 giving 12 times CO2 plus 13 times H2O plus 9.125 times O2 plus 103.87 times N2. So this is the chemical equation. Now it is mentioned that fuel is in liquid state. Correct. So that means I will say H enthalpy formation of the fuel, that is C12H26 will be equal to enthalpy of formation of fuel. Enthalpy of formation of fuel is C12H26, which is in a gas phase, minus HFG of C12H26. That is the latent heat of vaporization. This is nothing but latent heat of vaporization. So this is the equation. So you have to get the value of so the liquid value which is required is nothing but like this. So you can take this from the table, and HFG also is available in the table, and you can substitute this and find the value. So for dou decane, that is C12H26, I will say I will take the values of HFG as 256 kg per kilojoule per kg, or it will be equal to 256 into 170.337, that is molecular weight of C12H26. So that will be equal to, you can calculate this. So that is the value of HFG. Similarly, I can take the value of the enthalpy formation from the table. So I can calculate the enthalpy formation of the liquid dou decane. Okay. So here that is enthalpy formation of this gases will be minus 292,162 kilojoule per kilomole. Okay. So this is done. For other species, so this is actually standard heat is asked, standard heat of reaction is asked. So we can, so you can see that from the reactant side only the entire formation of dou decane is required. The product side the entire formation of CO2 and H2 are required. O2 and N2 will have 0 values. So now substituting this, taking the values from table and substituting, I can say delta HR will be equal to HP minus HR, which is equal to 12 times HF of CO2 plus 13 times HF of H2O minus HF of C12H26. This is into 1 into, I will say 1 into this. That's all. So substituting the values, 12 into minus 393,546 plus 13 into minus 241,845 minus, this is basically minus 292,162 minus 256 into 170.337. So I get a value of minus 7530768.7 kilojoule per kilomole of fuel. Now per kg of dodecane, delta HR will be equal to minus 44211 kilojoule per kg fuel. Okay, so negative then, because of this is the exothermic reaction, delta HC will be negative of this. So now delta HR per kg of O2, how will you find that? So now oxygen, mass of oxygen divided by mass of fuel will be equal to 27.625 into 32 divided by, that is number of moles of the oxygen stream, O2 plus 3.76 N2 into oxygen molecular weight is 32 divided by the molecular weight of the fuel 170.337. So this is nothing but molecular weight of the fuel, and this is the NO2 into molecular weight of O2. Okay, so substituting this value will be equal to 5.1897. So what is delta HR per kg of O2? That will be equal to minus 44211, this value per kg of fuel, divided by the value what we calculated now, that is 5.1897. That will be equal to minus 8519 kilojoules per kg O2. So in several ways we can find this, especially when you find the delta HR per kg of O2, you will see for several fuels the value will tend to a constant or a small range of variation only will be there. Now next is the value what we got, say 44211. So delta HC I will say will be equal to 44211. This is the negative of the delta HR, kilojoule per kg fuel. So this is actually called lower heating value. Why? Because the water vapor, this is HF of H2O, okay, that is for the HF vapor. The water vapor in the product is assumed to be in the vapor state, and the enthalpy of formation of the water vapor is taken into account. So the resulting value is called lower heating value, because still the water vapor has some energy which is the latent heat. By losing that, it will become liquid water. So now this is the higher lower calorific value. When you try to extract that also, the latent heat of the water vapor which is produced, that also will be added to the heat of the reaction or heat of combustion. So then we will get the higher heating value. So higher heating value is got by assuming all the water in the products is in liquid state. Okay, so that means here for 1 kg fuel, 13 kilomoles into molecular weight is 18 divided by 170.337 kg of water is produced. so which is equal to 1.3737 kg of water is produced. So that means I will say higher heating value HV, higher heating value will be equal to lower heating value plus HFG of H2O. Okay, this HFG should be in kilojoule per kg. So I will say into mass of water vapor produced. So that will be equal to 44211 lower calorific value plus 1.3737 which we have calculated into 44018 divided by 18, 010 by 18. So what is this? This is HFG in kilojoule per kilo mole, and this is the molecular weight in kilogram per kilomole. So when you substitute this, I get the value, higher calorific value is 47570 kilojoule per kg. Okay, so please understand that for the water vapor which is formed, when you cool it, obviously it will condense, but we cannot say that how much is condensing. So we have two extremes. Either assume that water is in vapor state always, which will yield the lower calorific value or lower heating value, or we can assume that all the water vapor has condensed into liquid water and calculate that so entire formation of liquid water has to be substituted, then you will get this value. So the difference is the latent heat of the water. So this is the problem. We will stop here and continue in the next session.